In this video, we'll learn about hypothesis testing. Consider a hypothetical scenario where you have joined the mobile phone manufacturer brand A as a business analyst. Now the company has come up with a new model called Max, and the popular sentiment among the company's engineers is that it requires 30 minutes of charging to receive a day's power. Based on this finding, the marketing team is planning to come up with a slogan that is a day's power with 30 minutes. Now you know that this value of 30 minutes is purely based on the popular sentiment among the company's engineers, and nobody knows for sure if this 30 minutes is valid number or not. You also learned from the office that one of the managers was assigned to check if this slogan would be valid, but when he picked up the Max phone, he found that it took 33 minutes to fully charge. So does this mean that the slogan is invalid? Obviously, the marketing team would not give up that easily, since in order to advertise, we usually want to use numbers that are easy to remember, such as 30 minutes, 60 minutes, and therefore similar figures. Now the marketing lead has approached you and asked you to conduct a proper statistical analysis such that we can actually quantify the validity of the slogan and find out how confident we are of the slogan being valid. Let's say we can acknowledge the validity of the slogan if we are able to prove with 95% confidence that the OnePlus Max phones can be fully charged within 30 minutes. Do you think you can solve this problem then? What if I tell you that you actually know how to solve this problem using the concepts that we already covered in the previous discussions? Well, the approach I would use is that I can collect a sample of say 100 Max phones. After collecting the sample, I would measure the time to fully charge each phone. Now, since the popular sentiment was that the phone charges within 30 minutes, my guess is that most of these values will fall in the range of 25 to 30 minutes. There may be also few phones that take more than 30 minutes, like the one that the manager had chosen, and some that may take less than 25 minutes to fully charge. With that sample, I can come up with a confidence interval for the average time taken by the phones to charge. And let's say that my 95% confidence interval comes out to be in the range of 24 to 29 minutes. In that case, I can confidently say that the belief that the charging time is below 30 minutes is correct if I consider a 95% confidence interval. However, if that same confidence interval on calculating comes out to say 26 to 30 minutes, then I can see that my confidence interval also contains values between 30 and 32 minutes. So I cannot say for sure that the charging time is below 30 minutes. Again, this is only considering a 95% confidence level. My conclusion would completely change if I were to consider a 90% or 99% confidence level. But do you feel this approach is logically correct? Yes, there's nothing wrong with this approach. In order to test the statement that the charging was below 30 minutes, I took out a sample and determined that the average charging time would lie between a certain confidence interval. However, maybe if I had considered a 99% confidence interval, then the range would increase to say 22 to 31 minutes. And then I cannot say anymore that the charging time is below 30 minutes given 99% confidence. So why we are discussing this? I gave you a small problem here that the objective was to test a certain claim that was made in the company. The claim was that the charging time of their latest mobile phone model is below 30 minutes. And using inferential statistics concepts, you understood how you would test this claim correctly or not. So you learned that hypothesis testing allows you to check the statistical credibility of the claims or assumptions that your organization has come up with. This claim could be claimed by a company or by a customer or just a form of popular belief that exists among the people. And using hypothesis testing, you can gather evidence in the form of a sample and then prove whether this claim should be rejected or not. As a result, hypothesis testing has been used in many businesses for making data-driven decisions rather than just relying on hunches. So let us look at some of the business decisions that can be taken using hypothesis testing. So one of the most common use cases of hypothesis testing is campaign effectiveness. Campaign analytics is very important, and using hypothesis testing, we can analyze whether the campaign that a bank or a company has launched is effective or not. So let's say a particular pizza company plans to launch a special campaign in Houston for new pizza that they have come up with. Now they want to check whether the sales through the campaign is significant or not. So they will divide the population into a test population and a control population. The test population is where you run the campaign, and the control population is where you don't run the campaign. So when they run the campaign on the test population and not on the control population, they measure the response rate of the customers in both populations. Now the assumption or claim in this case will be that campaign is not successful. And using hypothesis testing, we can use this response rate data to prove or disapprove this assumption and conclude if the campaign is actually successful or not. Such problems are known as A/B testing. and this is one of the most popular application of hypothesis testing. Apart from marketing campaigns, A/B testing is also used to compare different versions of web pages. So for example, here you can see two different versions of the same web page, and you want to know which version is more likely to get high response rates from the users. So like you saw in the previous example, you divide the population into two groups where they launch version A in group 1 and version B in group 2. And using hypothesis testing, you can easily conclude which version is more likely to get higher response rates. Apart from the applications you saw here, hypothesis testing can also be used to verify manufacturer or service provider claims. For example, suppose a manufacturer of light bulbs advertises that their light bulb has very long life of more than 5,000 hours. Then using the concepts in this module, you can easily test whether their claim is valid or not. Similarly, you will come across multiple applications of hypothesis testing in various fields, whether it will be quality control or efficiency management. As you get into this module, you will see many of these applications in the form of examples covered by us as a practice problem. So here we can clearly see the value brought forth by hypothesis testing. In this topic, let us understand hypothesis testing. Let us consider the same marketing example discussed earlier and see how the precision of a statement may influence the end consumer. Here, we'll test the claim that the new Max model takes exactly 30 minutes to charge. So this means that we'll reject the claim if our test suggests that the phone takes less than 30 minutes or greater than 30 minutes. So considering this claim, let's understand how to proceed with the hypothesis test. The general approach that we follow in hypothesis testing is that we start off by assuming that the claim is true. That is, the OnePlus Max model phones can fully charge in exactly 30 minutes. Now to start the hypothesis test, the first step is that you must define the null and alternate hypothesis. The null hypothesis, which we denote as H0, states that the default assumption about the population and is generally the status quo. So when I say status quo, we are referring to the initial belief that we had before we began our hypothesis testing. So in this example, the initial belief will be that the claim that the phone can fully charge in exactly 30 minutes is our null hypothesis. Now that our null hypothesis is clear, the next step is to state the alternative hypothesis. The alternative hypothesis is the claim that opposes the null hypothesis. It challenges status quo or the popular belief and is denoted by HA. In some places, it would be mentioned as H alpha or H1. Hence, in our example, the alternate hypothesis will be the statement contrary to the null hypothesis, and that is that the Max phones do not charge in exactly 30 minutes. So what happens if alternate hypothesis holds true? If the time taken is less than 30 minutes, then we need to take some action. This action would be that we revise this claim to some superior figure by finding the average charging time. Else, we could also alter our slogan and instead say that it charges in exactly 30 minutes. We can say that it charges less than 30 minutes. Whatever be it, it is good news for us. However, if the time taken is more than 30 minutes, then we should ask the engineer to fix the issue so that it charges exactly in 30 minutes. So you can see that in both cases, either the time taken is less than 30 minutes or greater than 30 minutes, some action needs to be taken. Thus, you can see that if the null hypothesis does not hold true, there is some action that needs to be taken. So let's write down the null and alternate hypothesis in the mathematical form. We have null hypothesis or H0 that charging time is equal to 30 minutes and alternate hypothesis or HA or H1 that charging time is not equal to 30 minutes. Let us continue to talk about hypothesis testing in further depth. Here, you saw the simple case of framing the null and alternate hypothesis. Now using this example, let us understand some properties of the null and alternate hypothesis that will help you frame them much better. Finally, the null and alternate hypotheses are always mutually exclusive events. So what does mutually exclusive mean? Mutually exclusive events are events that do not occur at the same time, as you can see in the Venn diagram here. For example, either the charging time has to be equal to 30 minutes, which is the event H0, or it cannot be equal to 30 minutes. Both statements cannot be true simultaneously because they are mutually exclusive. So if you were to write H0 and HA as charging time less than equal to 35 as H0 and charging time greater than 30 as HA, then automatically your hypothesis statements will be rejected because they are not mutually exclusive events. Second, the null and alternate hypothesis must be collectively exhaustive events. This means that at least one of these events must be true at any given time. This also means that these two events cover the complete sample space. So coming back to our phone charging example, we can see that at any point one of these two events must occur. That is either the charging time exactly equal to 30 minutes or it is not equal to 30 minutes. Thus, from my previous 2 points, you understood that the null and alternative hypotheses are always mutually exclusive and exhaustive. In other words, you can also say that they are completely complementary events and basically are always perfect opposites of each other. Now suppose the claim of the engineers was that the 1 plus max phone charges in less than 30 minutes, then the null hypothesis, which is the status quo, changes to H0, which will be charging time is less than 30 minutes, and alternative HA will be charging time is more than 30 minutes. Now, when we write this mathematically, one of these events must contain the equality sign, else these events will not be complement events anymore. Hence, the general rule that is followed by all statisticians is that the null hypothesis always contains the equality sign. So when writing this in the mathematical form, we can write it as H0 charging time is less than equal to 30 minutes and HA, which is charging time greater than 30 minutes. Similarly, if someone claimed that the phone takes at least 30 minutes to fully charge and you want to conduct a test to challenge this claim, then this is how you should frame your null and alternate hypothesis, meaning that it takes more than 30 minutes. Hence, the null hypothesis H0 becomes charging time is greater than 30 minutes and the alternate hypothesis becomes charging time is less than 30 minutes. So let us recap the key takeaways from this video. The null hypothesis is always the status quo, which means that it is the popular belief or the claim that you as the researcher want to challenge or prove wrong. And thus, since you are challenging the null hypothesis, the alternative hypothesis becomes the complement of the null hypothesis. And since you want to challenge the null hypothesis, you are essentially trying to prove the statement in the alternative hypothesis. In this video, we'll discuss about null and alternate hypothesis testing. The next thing you learned is that the null and alternate hypotheses are framed such that they are mutually exclusive and collectively exhaustive. And finally, the third point you learned is that the general convention we follow is that null hypothesis always contains an equality sign, while the alternate hypothesis contains an equality without the equal to sign. Now, before we take some examples to frame the hypothesis, we would like to discuss some important points to conclude the hypothesis testing. Let's go back to our charging time example where we wanted to test the claim made by the engineers that the max phone can charge in exactly 30 minutes. So this is how we framed null and alternate hypothesis. The null hypothesis or H0 is that charging time is 30 minutes. The alternate hypothesis is that charging time is not equal to 30 minutes. Now since only one of them must be true, so in order to find out which statement is correct, you perform some calculations. We'll discuss these calculations in later segments. And it turns out that the calculation is favoring the alternate hypothesis. Then the conclusion to your test should be you reject the null hypothesis or accept the alternate hypothesis. Since the alternative hypothesis in our test was that the charging time is not equal to 30 minutes, this is true, and depending on whether it is higher or lower than 30 minutes, we need to accordingly take the required action. Now what if your calculations suggest in favor of the null hypothesis? Remember that the null hypothesis was that the charging time is equal to 30 minutes. Does this mean that your null hypothesis becomes correct? No. You could say that I fail to reject null, or you could say that I reject the null and I reject the alternate hypothesis. But you cannot say that I accept the null hypothesis. But then you may be asking, what do you mean by fail to reject the null hypothesis? It means that whatever sample you have chosen don't have sufficient evidence to reject the null hypothesis. Doesn't that prove that the null hypothesis is true? Isn't it? It doesn't. Remember that your sample is only a subset of the population. Even a well-designed sample may not have the exact same characteristics as that of the population. There's still a lot of data about the population which we still don't know, and if we were to collect more sample data, then we may be eventually able to prove that the null hypothesis is wrong. So the null hypothesis could still be wrong. Let us discuss one small story to give us a better idea. There was a time when all swans in the world were supposed to be white or claimed to be white. This claim was made based on the fact that we have only seen white swans in that period in Europe for centuries. So the null hypothesis becomes that all swans are white. But then in 1697, a Dutch explorer found a black swan in Australia and brought back the black feathers to prove it. And because of this single data point, the null hypothesis got rejected. But until then, since we always saw white swans, our sample evidence was in favor of the null hypothesis. This is why we should say we failed to reject the null because there might still be a black swan out there to contradict the null. So the necessary key takeaway from this discussion was that there are only two possible conclusions from our hypothesis experiment. Either we reject the null, in which case we cannot accept the alternate, or we fail to reject the null on the grounds that we did not have sufficient evidence to reject it. Now that we have a good sense of how to frame our null and alternate hypothesis, in the next discussion we'll look at some of more real-life examples to frame the null and alternate hypothesis. Hypothesis testing part 2, critical value method. So let's get back to our business problem that we are trying to solve. You are working at Max Phone as business analyst. Now the company has come up with a new phone, and the popular sentiment among the company's engineers is that it takes exactly 30 minutes of charging to receive a day's power. Now, in order to test this claim, you have come up with the following null and alternate hypothesis statement. The null hypothesis states that the time needed to charge is equal to 30 minutes. The alternate hypothesis states the opposite. It can be written as the time needed to charge is not equal to 30 minutes. Let's move on to the next step of hypothesis testing. We'll start with the assumption that the null hypothesis is true, and then we'll try to disprove it. Your first task is to collect as much data as possible. For instance, let's say you sample 100 Mac smartphones. You time taken by them to go from 0% battery to 100% battery power. So this data consisting of 100 points becomes your sample. You now calculate the mean and standard deviation of the sample. On calculating, the sample mean is 30.37. For now, let us assume that based on the past research performed by the engineers, the population standard deviation is equal to 2.477. Remember, these figures only represent the sample you took and not the population. A crucial thing to understand here is that all 100 data points make up only one sample with a sample size of 100. The actual population, however, consists of a very large number of Mac smartphones. You cannot test them all. You'll assume that the population has a mean of 30 if the null hypothesis is true. Now you'll have to construct the distribution of the sample mean. Recall the center limit here. So how does this theorem help us here? We are going to use the distribution of the sample means to perform the hypothesis test. Once again, recall that you should choose a sample which is sufficiently large in order to be able to approximate the sampling distribution to a normal distribution. So let's list the measures you will use. The sample mean is 30.37. The standard deviation of the sample is 2.477. Now remember that the null hypothesis stated that the average charging time is 30 minutes. Hence the population mean is assumed to be 30 under the null hypothesis. Now using the center limit theorem, the sampling distribution of this population will have a mean which will be equal to the mean of the population, which is 30. The standard deviation of the sampling distribution will be the population standard deviation divided by the root of the sample size. Since we have assumed that the population standard deviation is known to us and is equal to 2.477, we can say that the standard deviation of the sampling distribution will be 2.477 divided by square root of 100, which is 0.2477. We now have a sampling distribution of mean 30 and standard deviation 0.2477, and since the sample size is 100, which is greater than 30, we can also say that sampling distribution follows a normal distribution. I can say that the sample mean of 30.37, which we previously calculated, lies in the distribution. So let's define the confidence level that is expected from the hypothesis testing. Previously, we discussed that the team is happy with the 95% confidence level. This means you are happy as long as the sample lies within this shaded region, which covers 95% of the overall area. Let's recall the properties of a normal curve. The mean lies at the center and divides the distribution into two equal houses. Roughly 68% of the area lies within one standard deviation from the center, 95% of the area lies within two standard deviations from the center, and 99.7% of the area lies within three standard deviations from the center. Now you have selected a 95% confidence level for this test. This means that the sample mean lies between plus minus 2 standard deviations. To be more precise, it lies between plus minus 1.96 standard deviations. Thus, 1.96 is your critical Z score. Let's check how many standard deviations from the center does our sample mean lie. This value is nothing but the Z score. It is an easy calculation. 30.37 minus 30 divided by 0.2477, and your answer should be 1.4937. Therefore, your sample mean lies 1.4937 standard deviations away from the center, and this is the Z score of the sample. Now your sample Z score is less than that of the critical Z score. This means your sample is closer to the center than your critical Z score. In such a case, you will fail to reject the null hypothesis, which means you will stick to the default belief that the Max phone takes 30 minutes to recharge. Again, this does not mean that we accept the null hypothesis. It only means that we don't have sufficient evidence to reject the null hypothesis. If the sample Z score was further away from the center than the critical values, reject the null hypothesis as it would fall outside the 95% region. So for example, if instead of 30.37, your sample mean had come out to be 30.62, then your Z score in this case will be 30.62 minus 30 divided by 0.2477, which is approximately 2.5. Then this would fall outside 95% region, and in that case you would be able to reject the null hypothesis. So let's quickly recap all the steps that we have used to solve them. We wanted to challenge the popular belief that the charging time is exactly equal to 30 minutes. The first step was to frame the null and alternate hypothesis. The second step is to decide the confidence level. The third step is to determine the critical Z score. The fourth step is to compute the sample Z score or the Z statistic for a general hypothesis test. Fifth and final step is to reach a decision and interpret the result. Now in our case, we tested for the deviation from the hypothesized mean, which was 30 minutes on both sides of the sample mean distribution. Hence, we saw that the rejection region lies on both sides of the mean of the sampling distribution. This type of test is called two-tailed test, as the null hypothesis can be rejected on obtaining extreme values on both sides of the curve. Hypothesis testing part 3, one-tailed test, critical value method. It's sometimes sufficient to test only one side of the sample mean distribution. This is called a one-tailed test. We'll see an example of this in this discussion. In the previous discussions, we learned how to conduct a simple hypothesis test. You may have noticed that in the max phone example, we performed the test on both sides of the normal distribution. That is, we would have rejected the null hypothesis if the same was significantly different in either direction. This is because we wanted to test if the time taken is exactly 30 minutes, but what if you are a max phone customer instead of a business analyst? Imagine that the OnePlus Max phone was advertising the phone using slogan "a day's charge in less than 30 minutes." And as their customer, you felt that this claim wasn't true. You now want to conduct a hypothesis test. So let's remember the steps that we discussed in the earlier discussions. Step 1 is to frame the null and alternate hypothesis. So let's formulate our null and alternate hypothesis. Recall that the original claim made by the company was that the charging time is less than 30 minutes. So our null hypothesis will state that the time needed is less than 30 minutes. The alternative hypothesis states that time needed is more than 30 minutes. Note that the null and alternate hypotheses are still perfect opposites of each other. So let's move to step 2. Step 2 involves deciding the confidence level. Let's say you still want to perform the test with 95% confidence. So this is step 2. Let's see step 3. The third step is to determine the critical Z value. Now this is where the problem will be slightly different from the earlier problem, where the null hypothesis stated that the charging time was exactly 30 minutes. In our current example, the null hypothesis states that the charging time is less than 30 minutes. This means that we can only reject the null hypothesis if we can prove that the sample mean that we get is significantly greater than 30 minutes. Hence, the rejection region is going to lie only on the right side of the curve, and such a test is called right-tail test. Let us compare this with the rejection region from the previous example. The shaded region in the image here still represents 95% of the area. As you can see, in the two-tailed test, you had 2.5% shaded area on the right side and 2.5% shaded area on the left side. In the case of a right-tailed test, the entire 5% will be on the right side. Thus, your critical Z value will not be the same as the one in the previous example. Previously, it was plus minus 1.96. Let's calculate the critical Z value for this case. Let's go to the Z table or R software to compute these Z values. Recall that we determine the Z value if we know the area under the curve to the left of the Z value. We know that the area to the left was Z value of 95%, as this is the confidence level given to us. So let us search for the Z value corresponding to this confidence level. So if you compute this Z value from the Z table or R software, you will get the value as 1.645 to be more precise. So now we have found out our Z value, which is a 1.645. As you can see in the figure, the rejection region will lie to the right side of the 1.645. Now that we have our critical Z score, let's move to the fourth step, which is to compute the sample Z score. From here, the rest of the process of the hypothesis test remains the same. So let's do the math for calculating the sample Z score. Let's say you manage to get the data of 100 phones and their respective charging times. So your sample size is 100 as it was before. Now let's say you calculated the sample mean and found it to be 30.79. Let's assume that we also know the population standard deviation from before and found it to be 2.477, which is the same value that we had considered when solving for the two-tailed test. So let's calculate our sample Z score. We know that sample Z score equal to sample mean minus hypothesized mean divided by standard deviation of population divided by square root of sample size. which here is 30.79 minus 30 divided by 2.477 divided by square root of 100. This value is approximately equal to 3.19. So we have our sample Z score as 3.19. This was our step number 4. Let's move to step number 5, which was to reach a decision and interpret the result. As you can see, our value of 3.19 is greater than the critical Z score of 1.645. Therefore, this value lies in the rejection region, and we can say that we reject the null hypothesis. What you just did was a right tail test. This is because the rejection region lies on the right side of the curve. So there are 3 types of tests that you will come across. First is the two-tailed test that you saw, where the rejection region lies on both sides of the distribution. Then you saw a problem where the rejection region was completely on the right side of the distribution, and you learned that such tests are called right tail tests. We also have a left tail test. This is when the rejection region lies on the left of the curve. Now let us discuss how we can tell the type of test and position of the rejection region by looking at the alternate hypothesis. If your alternate hypothesis has not equal to sign, then it is going to be a two-tailed test, and the rejection region will lie on both sides of the distribution. So if you recall the example where we had formulated the alternate hypothesis as charging time is not equal to 30, then the rejection region was on both sides of the curve, and we call it two-tailed test. Now let's take the next case. If your alternate hypothesis has a greater than sign, then you need to apply a right tail test, and the rejection region will lie on the right side of the distribution. So in this example, remember that the alternate hypothesis stated that the charging time is greater than 30 minutes. Hence, this will be a right tail test, and the rejection region is on the right side of the distribution. Then there's a third type of test, which is left tail test. If your alternate hypothesis has a less than sign, then you know that you need to apply the left tail test, and the rejection region will fall on the left side of the distribution. Let us consider an example of this. Let's consider the hypothetical case where you may want to apply the left tail test. Cadbury Chocolate states that the average weight of one of its chocolate product, Dairy Milk Silk, is 60 grams. As an analyst in the internal quality assurance team, you would like to test whether the weight is lesser than 60 grams or not at 2% significance level. Since you want to test whether the weight is less than 60 grams, this will be your alternate hypothesis, and the null hypothesis will become mu is greater than 60. You can say that this will be a left tail test because the alternative hypothesis contains less than sign. Can you try solving this question? Let us explain the approach. You learned that any hypothesis test can be solved in 5 steps. All the steps will remain the same except for the step 3, which is where you determine the critical Z score and rejection region. Since this is a left tail test, the rejection region will lie on the left side of the curve, as you can see in the shaded area of this curve. Since we are considering a 2% significance level, hence the area of this colored region will be 0.02. Hence the critical Z value will be the value corresponding to this value of 0.02, and your rejection criteria will be to reject the null hypothesis if your Z statistic lies outside this rejection region. This means that you can reject the null hypothesis if you calculated Z statistic greater than your critical Z value. In the next set of discussions, we'll be learning about another approach known as p-value method. Now let's understand the p-value method in hypothesis testing part 4. Now that you are comfortable with the overall process of hypothesis testing, I will introduce us to a new approach called p-value method. Both the critical value method and p-value method give the same results when testing hypothesis. In the critical value method, remember that we had to compute two values to test statistic and the critical value corresponding to the given confidence level. However, the p-value method has the advantage that you just need to compute one value, and that is the p-value. Hence, most statistical software and calculators use the p-value approach for hypothesis testing. We'll take up the same problem of max phone charging time for the p-value method. Recall, we wanted to test the claim that the smartphone model requires exactly 30 minutes of charging to receive a day's power. We also know the population standard deviation, which is 2.477, and it is also given that the sample mean of the 100 data points that we considered is 30.37. So using this information, let's solve this problem with the p-value approach. We'll solve this step by step like we did for the critical value. However, unlike the critical value method where we had 5 steps, we have divided the complete process of p-value method in 4 steps. Let us explain what these 4 steps are. Step 1 is to state the appropriate null and alternate hypothesis. We know that the null hypothesis was that mu equal to 30 minutes, and the alternate hypothesis was that mu was not equal to 30 minutes. Mu here is the mean. Now step 2 is here you decide the level of significance. As you already know, the level of significance is 5%, or in other words, the confidence level is 95%. The most important step for p-value method is step 3 is to compute the test statistic and calculate the p-value from there. Let us first calculate the test statistic. As you know, the test statistic is nothing but the z statistic or the sample z score that we calculated earlier. The formula for calculating z statistic given by samples z score equal to x bar minus mu divided by sigma by rho 10. Using the values that we mentioned above, we know z statistic comes around to 1.4937. How do we calculate the p-value? Graphically, the p-value is the area in the tail of the probability distribution. For our max phone example, since this is a two-tailed test, we would need to calculate the area at both tails. Since our z score, our z statistic is 1.4937, the p-value will be the area from this minus infinity to minus 1.4937 and plus 1.4937 to plus infinity. But since the curve is symmetric on both sides, we can directly calculate the area at any one tail and then double it in order to calculate the p. So let us calculate the area on the left tail. At the left tail, the z value is minus 1.4937. Now let us go to our z table to calculate the area on the left tail. So here we have the z table. First let's break z score into minus 1.4 and 0.09. So I'll search for the corresponding value to minus 1.4. We can use z table or R software to compute these values and get the value, which is 0.06811. Doubling it turns out to 0.136. So now we have our p-value and we can complete the third step. In the final step, we reach a decision and interpret the result. If the p-value is less than or equal to alpha or the significance level, then we reject the null hypothesis. Remember that alpha is your significance level. So since our confidence level is 0.95, alpha equal to 0.05. Hence, our condition for rejecting the null hypothesis is that our p-value should be less than or equal to 0.05. Now our p-value is 0.136. However, since 0.136 is not less than 0.05, we fail to reject our null hypothesis at 95% confidence level. Now let's see how we calculate the p-value based on the type of test. For a two-tailed test, then the p-value falls on both sides of the curve. This is where you are calculating p-value for a two-tailed test. For the left-tailed test, the p-value will be on the left side of the curve. So let's say your test statistic is some value z, then the cumulative probability that you get from the table will be your p-value. Let's see for the right-tailed test. For the right-tailed test, the p-value will be on the right side of the curve. So if the value of the test statistic is z, then the cumulative probability from the table will give you the area to the left of z. Since the p-value is the area to the right of the curve, hence your p-value will be 1 minus the cumulative probability that you calculate from the table. Once you have the p-value, then the condition for rejecting the null hypothesis remains the same for whatever test it is, be it right-tailed, left-tailed or two-tailed. The condition is always that you reject the null hypothesis if your p-value is less than or equal to alpha. Summary and concluding remarks. In this discussion, we learned about the need for hypothesis testing. We realized that we cannot rely on hunches to make business decisions, since the stakes are often too high and mistakes needs to be avoided. Hypothesis testing gave us a way to check all the claims with statistical rigor. We learned that null hypothesis is defined as the assumptions you are testing, and the alternate type hypothesis is defined the opposite. You then saw an example where you used a hypothesis test to verify max phone claims. Here we define the null hypothesis as the time needed to charge is equal to 30 minutes, and the alternate hypothesis is the time needed to charge is not equal to 30 minutes. You then learned how to collect several data points that comprise a single sample. You found the z-score of the sample on the sample means distribution using concepts learned from the previous discussions. You also learned about confidence levels and critical z-scores associated with them. You rejected the hypothesis if your sample z-score was further away from the hypothesized means than the critical z-scores. This approach is known as critical value method. You then saw another measure known as p-value, which is more intuitive than z-score and can be used directly to find the highest confidence level at which the test can be rejected. You learned the p-value can be easily visualized as the probability of null hypothesis being the true, and thus a lower p-value means a higher chance of the null being false. The p-value can be used to directly find out the confidence levels at which the null hypothesis can be rejected, but now we know the basis of hypothesis testing.